All right, guys, how's it going? Hope all is going well. So today we are continuing our notes, talking about how heat is used in changing of stages or states. So solid, liquid, gases. How does that all occur? Well, it's because of our best friend heat. So we're going to go ahead and get started. Make sure you have your notes out. We have numbers 40 through 42. 40 through 42. So, have you guys ever placed an ice cube in a warm room, or maybe you're walking outside in the summer here, and then like you have an ice cube in your hand for whatever reason, and it melts, right? So basically, like we've talked about in the previous discussions, is that the ice is absorbing heat. So it's absorbing the heat, which would be an endothermic, and it will begin to melt. So that's why ice melts, is because it is absorbing heat. So you can tell that whenever you're on your next date. But basically, the temperature of the ice in the liquid water remains at about 0 degrees Celsius, which is freezing until all the ice has melted. That's kind of an interesting concept there, that they will stay at the same temperature until all the ice has melted, and we'll talk about why that is in just a minute. So just like ice cubes, all solids absorb heat as they become liquids, no matter what it is, whether it's, I don't know, what's a liquid? I don't know, alcohol. If you freeze alcohol and it melts, right, it is absorbing heat. And so anytime we have a change in state, the reason that it goes from solid, gas, liquid, all those, is because of a gain or a loss of heat. Okay, and the way that we can measure that, if you remember, we can't measure heat itself, but we can measure the effects of it, which is temperature. And so when something is changing phases, the temperature remains constant until it officially changes into that next stage. So if you have a liquid and you're trying to boil it, like water, you're trying to make pasta or whatever, you're boiling water, the temperature of that water is going to stay the same until it turns into a gas. Kind of weird. You think it would increase, but it's actually going to stay the same until it changes state, and we'll talk about that in just a minute. But we have numbers 43 and 44. Okay, so the first thing we're going to talk about is something called the molar heat of fusion, and it is written as a delta H with the FUS. So if you remember, delta means a change and H means heat, so a change of heat. Okay. So the heat absorbed by 1 mole of a solid substance as it melts at a constant temperature is called the molar heat of fusion. So basically, this is something melting. So if you have a mole of butter, for whatever reason, and you are trying to melt it into liquid butter to brush on your croissants, the amount of heat that it's going to need to absorb is what we call the molar heat of fusion. Now, the exact opposite happens with molar heat of solidification. So instead of going from solid to liquid, it's going from liquid to solid. So that makes sense. Molar heat of solidification is becoming solid. And so whenever, if you have a mole of a liquid substance and you're trying to solidify it, turn it into a solid, the amount of heat that needs to be lost is the molar heat of solidification. So molar heat of fusion, the amount of heat absorbed, molar heat of solidification is the amount of heat lost. Okay, and so what we see is that the quantity of heat absorbed by melting is the same as the amount of heat released. So whether it's going from solid to liquid or liquid to solid, it doesn't matter. It's either going to need to gain or lose the same amount of energy. And we can see that here. This is what this equation here means. So the amount of heat for fusion, which is melting, is equal, but a negative, because it's losing, the amount of heat needed to go from a liquid to a solid. And we can see that a little bit more here. So here we have the amount of heat needed to go from a solid to liquid water. So if you have an ice cube and you want to go to liquid water, the amount of heat needed is 6.01 kilojoules per mole. So that's how much energy or heat that solid water is going to need to gain to turn into a liquid. And what's interesting is that we see the exact opposite here. So to go from liquid to solid, we need it to lose it needs to lose 6.01 kilojoules. So this is gaining, and if you see a negative, that means it is losing. So that's how much heat it needs to gain to change states, and this is how much heat it needs to lose to change states. Okay, and we've got 45 through 47. 45 through 47. Now, of course, there's more than just solids and liquids. There's also liquids and gas. And so the liquid that absorbs heat at the boiling point becomes vapor, right? So if you are boiling water, it is absorbing a lot of heat and turning into vapor. And this is what we call molar heat of vaporization. So if you have a mole of water and you want to boil it, the amount of heat you'll need is called the molar heat of vaporization, right? To turn into a vapor. And the molar heat of vaporization is 40.7 kilojoules per mole. Let's think about that for just a sec. I'm going to change here. So to go from solid to liquid, it needed 6 kilojoules. But to go from liquid to gas or vapor, it takes 40.7 kilojoules, way more energy. I want you to kind of think about that, and we'll go over why that is in a minute. It's kind of interesting that it takes a lot more energy to go from a solid to a liquid, or sorry, to go from a liquid to a vapor than from a solid to liquid. So it takes a lot of energy there. So here we can see, here are some various substances. So ammonia, super stinky. To go for, so the molar heat of fusion, so to go from a solid to liquid, it needs 5.66 kilojoules per mole. But to go from a liquid to a gas or a liquid to a vapor, it needs 23.3 kilojoules. And we can see that for all of these, the amount we need to go from solid to liquid is significantly less than the amount of energy we need to go from liquid to gas. Kind of interesting. Okay, so we've got numbers 48 through 51. 48 through 51. Now, of course, there's an opposite of vaporization. So there's molar heat of fusion going from solid to liquid. There's molar heat of solidification going from liquid to solid. We have molar heat of vaporization going from liquid to gas. And then condensation is going from gas back to liquid. So the molar heat of condensation, so this is how we shorten it, delta H, change in heat, cond, meaning condensation, is the amount of heat released when 1 mole of a vapor condenses. Okay, so it's just like what we see before. And like we saw with the solids and liquids, liquid to solids, the amount of heat we need to release to go into the amount of heat we need released to go into a condensation state to go from gas to liquid is the same exact amount as the amount of heat we need to absorb. So we can see that same exact idea as with going from solid to liquid, liquid to solid. We need the same amount of energy, either gain or loss. Same exact idea goes with liquids going from liquid to gas or gas to liquid. Same exact quantity of heat needed to either be absorbed or released. Okay. So we can see, if we look at this chart, and actually number 52, kind of want to take a look at this chart here. So here, this is what we call a heating curve. So we can see how much energy is needed to go into the different states. So from solid to liquid, this is the amount of heat needed. Okay, so what do we notice about this versus the amount of energy needed or the amount of heat supplied to go from liquid to vapor? So the going from solid to liquid or liquid to solid, really not that much energy, but to go from liquid to vapor, it takes so much energy, which is, it makes sense. So if you were to put your hand, I don't know, you're trying to boil water, and so you have, or no, I'm sorry, you have ice cubes and you're trying to turn it into a liquid. You just like stick your hand in it and the ice cubes and then wait for it to melt. It's not like gonna hurt your hand that much, like it'll get cold. But if you stick your hand over boiling water and all that steam is hitting your hand, that hurts really bad. Steam burns are the worst type of burns you can get. And that's because it needs so much energy. It's releasing so much energy. And that's why vapor burns are so much more potent in hurting someone than just changing from solid to liquid. So much energy being released or absorbed. So that's really what this heating curve is telling us, is the amount of energy we need to change states. Okay, number 53 says reflect back on the molar heats, write a paragraph. So go ahead and write a quick little paragraph talking about all the different molar heats: condensation, vaporization, solidification, and fusion, and how they are similar and how they are all different. So go ahead for number 53, answer that. And we're gonna move on here to 54 through 55, or sorry, through 56, 54 through 56. Okay, so how many of you guys have ever used a hot pack or a cold pack? I know I have. So you like hurt yourself, and so you get a pack of ice and you put it on your leg or whatever, and so you can feel it getting hot or cold, right? And so basically what you're feeling is the formation of a solution. So think about hand warmers. I get cold easily. So whenever I go camping, I have a sorry, a hot pack to like shove in my sleeping bag and put in my pockets and stuff. And so a lot of them have like a little thing that you break, or like they do a chemical reaction when they interact with the air that makes it warm. And that is a solution. And so basically you feel the enthalpy or the heat changes that occur when a solute dissolves in a solvent. So what a solvent is, it's basically something that can dissolve a substance. And a solvent, or solute, is something that is dissolved in a solvent. So that's basically when a solute, something is dissolved inside of something that dissolves things. That's basically what that says there. So the molar heat of solution is just like the condensation, vaporization, all that stuff. It's just instead of going from solid to liquid or liquid to gas or whatever, it's talking about the formation of a solution. So for example, those hot packs, when you break the little thingy inside of it and it gets all warm, that is what's happening. It's an enthalpy change. It's a change of heat that you can feel. And that amount of heat needed is what we call a molar heat of solution. So that is all the notes for today. And we are almost done with notes already. Wow. All right. Have a good day.